It was American author Ralph Waldo Emerson who said, "Money often costs too much." In this lesson, we're going to write, graph, and interpret the expense function. We're going to write, graph, and interpret the revenue function. We're going to identify the points of intersection of the expense and revenue functions. We're going to identify break-even points and explain them in the context of the problem. And we're going to factor a quadratic using the method of completing the square. All to answer the question, how can expense and revenue be graphed? Before we get into it, let's take a look at warm-up number 2. What are the coordinates of the x-intercept of this equation? Well, to start with, I'm going to write this in factored form. And I can see that this is going to be x plus 5 times x plus 3. This means that one of the x values will be negative 5 and one of the x values will be negative 3. So the x coordinates are going to be negative 5, 0 and negative 3, 0. Now let's take a look at a problem you will be able to do by the end of this lesson. The revenue and expense functions from the examples above are graphed on the same set of axes in this graph. The points of intersection are labeled A and B. Explain what points A, B, C, and D represent in the context of the problem. When the revenue and expense functions intersect, revenue and expense are equal. These are break-even points. Notice that there are two such points. Before intersection point A, the expense is greater than the revenue. The first break-even price is approximately $8.08. The second is approximately at $58.92. From point A to point B, the revenue is greater than the expense. To the right of point B, the expense is greater than the revenue. Points C and D are the coordinates of the roots of the revenue equation. The graph confirms the fact that when P is equal to 0 and P is equal to 60, there is no revenue. The total expense for the production of a certain item is the amount of money it will cost to manufacture and place it on the market. One contributor to consumer demand is the price at which an item is sold. Expense relies on the quantity produced and the demand relies on the price, so the expense function can be written in terms of price. Recall that revenue is the total amount a company collects from the sales of a product or service. Revenue depends on the demand of the product, which is a function of the price of the product. The relationship between price, demand, expense, and revenue can better be understood when the functions are graphed on a coordinate plane. Both the demand and the expense functions are linear. However, as you will see, the revenue is a nonlinear function when it is expressed in terms of price. That is, the graph of the revenue function is not a line. The revenue function has a variable raised to an exponent of 2. So it is a second-degree equation and known as a quadratic equation. A quadratic equation can be written in the form y is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not 0. The graph of a quadratic equation is a curve called a parabola. In the graph shown, the horizontal axis represents the price of an item, and the vertical axis represents the revenue. If the leading coefficient A is positive, then the parabola opens upward. In the graph, the parabola reaches its lowest point or minimum. This point is the vertex of the parabola. If the leading coefficient is negative, then the parabola opens downward. The downward parabola shown models a revenue function. In the graph, the parabola reaches its highest point or maximum at its peak. This point is also known as the vertex of the parabola and would yield the price at which revenue can be maximized. The axis of symmetry in a downward or upward opening parabola is a vertical line that can be drawn through the vertex of the parabola so that it bisects halves of the parabola are mirror images of each other. The x-coordinate of the point of the horizontal axis through which the axis of symmetry passes is determined by calculating negative b over 2a. The equation x is equal to negative b over 2a is the equation of the axis of symmetry. The graphical relationship between revenue and expense reveals the information that can be helpful to a business. Now let's write, graph, and interpret the expense function. A particular item in the Picasso Paints product line costs $7 to manufacture. The fixed costs are $28,000, and this is the demand function on the screen, where Q is the quantity the public will buy given price P. Graph the expense function in terms of price on a coordinate plane. The expense function is that E is equal to 7Q plus 28,000. Now we're going to substitute Q to find the expense function in terms of price. So this means that E is equal to 7 times negative 500p plus 30,000 plus 28,000. Now distributing and combining like terms means we're going to get E is equal to negative 3,500p plus 238,000. The horizontal axis represents the price and the vertical axis represents the expense. Both variables must be greater than 0. To determine the viewing window, find the points where the expense function intersects the vertical and horizontal axis. Neither P nor E can be 0 because the price of 0 and the expense of 0 would be meaningless in this solution. But you can use P is equal to 0 and E is equal to 0 to determine the appropriate viewing window. So by looking at this equation, if P was equal to 0, then E would be equal to 238,000. If E were equal to 0, then 0 would be equal to negative 3,500p plus 238,000, which means 3,500p is equal to 238,000, which means that P is equal to 68. Use the intercepts to determine the size of this viewing window. In order to get a full picture, we're going to use window values that are slightly greater than the intercepts. Choose the appropriate scale for each axis. In this case, set the horizontal axis to 0 to 70 with the scale of 10 and a vertical axis at 0 to 240,000 with a scale of 50,000. So we can say 10, 20, 30, 40, 50, 60, 70. This would mean the E-axis intercept will occur at 238,000, and that the P-axis intercept will occur at 68. So even if drawing it by hand, we can get a pretty good idea of what it's going to look like. Let's check our understanding. An electronics company manufactures earbuds for portable music devices. Each set costs $5 to manufacture, has a fixed cost of $20,000, and this is the demand function. Write the expense function in terms of Q and determine a suitable viewing window for that function. Graph those expenses. So we're going to start out by writing that expense function where E is equal to 5 times Q plus 20,000. Now we're going to substitute that Q value that we have so that E is equal to 5 times negative 200p plus 40,000 plus 20,000. We're going to distribute and combine like terms so that E is equal to negative 1,000p plus 220,000. Next, we'll go ahead and figure out what happens if P were equal to 0. And if that happened, then E would be equal to 220,000. And if E was equal to 0, then we would get that 0 is equal to negative 1,000p plus 220,000. And solving for P, we would get that P is equal to 220. So on our graph, where E represents the y-axis and P is the x-axis, we're going to go ahead and use 50s. So we get a 50, 100, 150, 200, 250. Now we know on this line we're at 220. And for the e-axis going all the way up to 220, we'll say 50,000, 100,000, 150,000, 200,000, and 250,000, knowing that that E-intercept occurs at 220,000. This gives us our line. What is the revenue function for the Picasso Paints product? And write a revenue equation in terms of price. So the revenue is the product of the price and the quantity, meaning that R is equal to P times Q. The quantity Q is expressed in terms of the price, so the expression can be substituted into the revenue function. Now we know from example 1 that Q is equal to negative 500p plus 30,000. This would mean that we could substitute Q into our revenue equation, giving us R is equal to P times negative 500p plus 30,000, and distribute that to get negative 500 p squared plus 30,000. The revenue function is a quadratic equation in the form y is equal to ax squared plus bx plus c, where a is a negative 500, b is 30,000, and c is 0. Because the leading coefficient is negative, the graph of the parabola opens downward. Let's check our understanding of this. Determine the revenue for Picasso Paints in example 2 if the price per item was set at $25. So this means that P is equal to 25. And we already know that revenue is equal to negative 500 P squared plus 30,000 P. So we're going to substitute 25 into this equation in place of P. By simply using our calculator, we can get that R is equal to 437,500. Graph the revenue function of Picasso Paints in example 2 on a coordinate plane. The graph opens downward. It has a maximum height at the vertex. And to find the x-coordinate of the vertex, we're going to use the axis symmetry found with b is equal to 30,000 and a is equal to negative 500, using the equation negative b over 2a. So we're going to substitute to get negative 30,000 divided by 2 times negative 500. And this is going to give us 30. So the axis of symmetry passes through 30 on the horizontal axis. To determine the height of the parabola at 30, we're going to evaluate the parabola when P is equal to 30. So if P is equal to 30, we're going to say R is equal to negative 500 times 30 squared plus 30,000 times 30. This is going to give us a revenue of $450,000. This means this point right up here, straight across, this would be at $450,000. When the price is set at $30, the maximum revenue is $450,000. The vertical axis must be as high as the maximum value. For the viewing window, use a number slightly greater than the maximum value, such as 500,000, so that you can get the entire picture of the graph. Use the same horizontal values as the axis used in the expense function. Let's check our understanding. Use the graph from example 3. Which price would yield the higher revenue, $28 or $40? So we can see the axis of symmetry occurs when P is equal to 30. So if we just look at what happens when P is equal to 28, we can see generally how close to the price it would be. When we look at the 40, we can see how much lower that is. Because $28 is closer to $30 than $40, it will yield a higher point on the parabola. You can test this statement by substituting any other value you would think of to see, does it always work? Would that still happen if you tried $6? A downward parabola in the first quadrant will intersect the x-axis in two places. The x values of those intersection points are known as roots or zeros of the equation. In example 3, rather than ordered pairs in the form of xy, the ordered pairs in the problems were PR. So the two roots of the quadratic equation will each be in the form of P0. The root can be found in a number of ways. Since the r value of the coordinates of the root is 0, substituting r for 0 in the revenue function, where 0 is equal to negative 500 p squared plus 30,000 p. In previous math courses, you learned how to factor quadratic equations. Keep in mind that not all quadratic equations are factorable. The equation that you now have is in the form of 0 is equal to AP squared plus BP plus C, where A is not 0 and C is not 0. First, look for a common term that can be divided out or factored out of each term of the right side of the equation. Note that this process is the reverse of the distributive property. Since both negative 500p squared and 30,000p are divided by negative 500p, we're going to factor that out to get 0 is equal to negative 500p times p minus 60. You can check your work using the distributive property to verify that negative 500p times p minus 60 is equal to negative 500p squared plus 30,000p. Recall that if a times b is equal to 0, then a is 0, b is 0, or both a and b are equal to 0. We're going to apply that property here, that zero product rule. So negative 500p being equal to 0 means p equals 0. And p minus 60 equal to 0 means that p is equal to 60. The roots of the revenue equation are 0 and 60. In the context of the problem, it can be interpreted as there will be $0 in revenue when the price is 0 and $60. The quadratic formula can be used to find the roots of quadratic equations. The quadratic formula for ax squared plus bx plus c is equal to 0 when a is not 0 is that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where that plus or minus reads two solutions, both the plus of the root and the minus of the root. Use the quadratic formula to find the roots of negative 500p squared plus 3000p is equal to 0, where a is negative 500, b is 30,000, and c is 0. So we get p is equal to negative 30,000 plus or minus the square root of 30,000 squared minus 4 times negative 500 times 0. This is going to give us p is equal to negative 30,000 plus 30,000 divided by negative 1,000, and that is going to give us p is 0. It will also give us negative 30,000 minus 30,000 divided by 1,000, and that will give us a positive 60. Notice the quadratic formula yields the same roots as determined when factoring the quadratic equation. Recall from a previous math course that a perfect square trinomial can be written as the square of a binomial. For example, x squared plus 10x plus 25 is a perfect square trinomial since it can be written as the sum of x and 5 squared. The general format of a perfect square trinomial is that a plus b squared is equal to a squared plus 2ab plus b squared. The method of factoring by completing the square allows you to mathematically manipulate a non-perfect square trinomial so that one side of the equation becomes a perfect square trinomial. This will make solving for the roots an easier process. Let's examine the following steps using the method of completing the square. Find the roots of the equation x squared plus 6x minus 2 is equal to 0. We're going to move the constant term to the other side of the equation by adding 2 to both sides. We're going to add a constant to both sides of the equation so that the left-hand side becomes a perfect square trinomial. To determine the constant term, take half of the coefficient of the original middle term, that x term, and square it. So half of 6 is 3, and 3 squared is 9. This gives you the number to add to both sides, giving us x squared plus 6x plus 9 is equal to 2 plus 9, which is 11. The process now assures that you have a left side is a perfect square trinomial, as you can see here. We get x plus 3 squared is equal to 11. Solve by taking the square root of both sides. Remember that in doing so, you must account for both positive and negative possibilities. So x plus 3 is equal to the positive root of 11, and x plus 3 is equal to the negative root of 11. Now, when x plus 3 is equal to the positive root of 11, we get that x is approximately 0.3166. And when x plus 3 is equal to the negative root of 11, we get that x is approximately equal to negative 6.3166. Now, let's factor quadratics using the method of completing the square. We're going to use the method of completing the square to find the roots of the revenue equation determined in example 3. The revenue equation from example 2 is r is equal to negative 500 p squared plus 30,000 p. So we're going to let r equal 0, giving us 0 is equal to negative 500 p squared plus 30,000. We're going to divide everything by negative 500, giving us 0 is equal to p squared minus 60p. Now we're going to determine the constant that must be added to both sides of this equation to make it a perfect square trinomial. So negative 60 divided by 2 is going to give us negative 30. But we're going to want to go ahead and square that to give us 900. This means that 900 is equal to p squared minus 60p plus 900. This is now a perfect square trinomial that can be factored into p minus 30 squared, and that's equal to 900. Taking the square root of both sides, we get plus or minus 30 is equal to p minus 30. This means that we have two possible answers here. One is that there is a positive 30 equal to p minus 30. The other is that there is a negative 30 equal to p minus 30. Solving the right one for p, we would add 30 to both sides, getting that 60 is equal to p. And solving the negative version, we would add 30 to both sides, getting that 0 is equal to p. So the roots of the revenue equation are again found to be p equals 0 and p equals negative 60. Let's check our understanding. Select any two methods that have been shown to find the roots of this function. Well, to start with, I know that we're dealing with when r is 0. So I get 0 is equal to negative 200 p squared plus 16,000 p. If I divide everything by negative 200, I get that 0 is equal to p squared minus 80p. I can then factor the p out of this to get 0 is equal to p times p minus 80. Now the zero product rule means that this p is 0 and that this p is 80. So the coordinates of the roots are 0, 0, and 80, 0. Now, let's identify the points of intersection of an expense and revenue function. The revenue and expense functions from the examples above are graphed on the same set of axes in this graph. The points of intersection are labeled A and B. Explain what points A, B, C, and D represent in the context of the problem. When the revenue and expense functions intersect, revenue and expense are equal. These are break-even points. Notice that there are two such points. Before intersection point A, the expense is greater than the revenue. The first break-even price is approximately $8.08. The second is approximately at $58.92. From point A to point B, the revenue is greater than the expense. To the right of point B, the expense is greater than the revenue. Points C and D are the coordinates of the roots of the revenue equation. The graph confirms the fact that when p is equal to 0 and p is equal to 60, there is no revenue. Let's check our understanding. Why would charging a price of $7.50 or $61 not be the best interest of the company? At both prices, the revenue is less than the expense. The price of $7.50 is too low for the incoming revenue to make up for the outgoing expenses. The price of $61 may be too high for consumers and would decrease the demand on the product. Therefore, the fewer items being sold, the revenue would be less.